Okay, so as Jens mentioned, today I'm going to talk about exceptions, and I hope you find this topic interesting. But let me start with introducing myself. So my name is Inbal Levi. I'm a C++ enthusiast. I'm also an embedded software engineer at SolarEdge, and I'm working on smart home devices. I'm one of the organizers of Core CPP conference and user group. As Jens mentioned, a member of Workgroup 21 and one of the founders of the Israeli National Body. So we just voted on C++ 20. That's I think it's a great start. And I've studied physics. I also love math. So if anyone wants to talk with me about math later, you're most welcome. So let's start with motivation. So exceptions are a mechanism that is widely used on C++ in general. But you might be surprised to find out that quite a lot of the developers don't use the exceptions mechanism fully. You can see here a survey from ISO that suggests that around 54, more than half of the developers don't use exceptions freely in their code. And this is a survey that I did. You might have seen it on Twitter via the Core CPP account. That you can see here that also quite a lot of developers are working on embedded systems or performance sensitive systems. And so I'm sure that if I would have asked you, you would say that similar percentages are working on exceptions. So I think it's very interesting. So as I mentioned, many industries and they don't really use exceptions mechanism as fully as we would hope. And the error handling mechanism, you might be surprised, but it's also been addressed quite recently by the Direction Group, which is a group of the people in the committee that are mostly they're trying to address the core topics of C++. And they have addressed the error handling mechanism via contracts, which is also a way to it relates to preconditions, but it's also a way to address problem errors in the code and to deal with the decision making result from it. Another thing, sorry, slides. Another thing that was also published quite recently was a paper by Herb Sutter, and I'm sure you all heard of it, Zero Overhead Deterministic Exceptions, Throwing Values. And in the last meeting, in the last Workgroup 21 meeting that took place in February, we also saw a very interesting paper, the exception, low-cost deterministic exceptions for embedded systems. So it was also discussed quite widely. So to conclude, I expect that the error handling mechanism is going to be addressed widely in the near future in C++ standard. So the outline for my talk is we're going to start with history and domain. We're going to look at exceptions overhead. We will overview the design. Then we're going to go over some alternatives, both proposed and things that are potentially might be potential in the future. And then we're going to see some directions for the future for you if you want to be involved, if you take interest in this topic. And I really hope that you'll find this inspiring. So I just want to have a few disclaimers. This is not a talk about best practices of exception usage. There is a very good talk by Klaus that I think, it was on CPP CPPCon 2020. So if you're interested in how to best use exceptions in your code, you're most welcome to watch that talk. And it's also not a talk about a library. The code here is POC. And concurrency, I haven't addressed concurrency since, at least in my industry, it's less relevant. But I'm sure that's also a very interesting topic you could expand on. And I'm also addressing some of historical references, but I wasn't there, so take this as it is. So let's briefly go over the history, and I'm not going to go into too many details, but on the history of exceptions. But I do want to have some points. So in the beginning, we had C. Then came C with classes, and then came C++. But actually, then came C++ with exceptions, because exceptions were dealt with very early in the design of the language. So just to go back a few years, we had two main ways to deal with errors. So the first one was error codes, just like we do on C, and currently also doing on C++ in some cases. And the second way to deal with errors was by using global. It could have been error no, it could have been some user-defined global. These are just general design guidelines, but we had those two main ways to deal with errors. And just notice that here, for the return value, we have to propagate the return value throughout the calls. So if bar was calling foo here, then we have to take this all the way up to the main. And by using global, we could basically skip. So the functions that weren't interested in the result didn't have to address this, didn't have to use this mechanism. So I want to quote from Design and Evolution. I think it's a great book. So in the original design of C++, exceptions were considered but postponed because there weren't time to do a thorough job of exploring the design and implementation issues, and because of the fear of the complexity that might add to an implementation. So it's true that exceptions are not a simple topic, and I think it's very interesting that even in those years, and remember that this was really in the beginning of the design of the language, the problems already came up. Also, in particular, it was understood that poor design could cause runtime overhead and significant increase in porting times. So, as I mentioned, they were considered very early. And on the first standard of C++, you can already see that there was a section addressing exceptions. So the following exceptions were made regarding the exceptions usage. So exceptions are used primarily for error handling. And they're also rare, and comparing to regular functions and regular logics. They, as I said, they occur infrequently, and they're a language level concept. So again, this is from, I haven't mentioned that, but this is from the first paper that was trying to design the first exception handling mechanism, which eventually led to the version that we had in the first standard. So let's briefly look at the exceptions overhead. And again, this is not a talk that suggesting or trying to address whether to add or not to add exceptions in your code. This is, of course, your decision, but I'm trying to focus on the overhead that is created by them and how can we minimize that. So first of all, just to mention, the main difference between C and C++ is the cleanup progress. So basically C++, by having constructors and destructors, adding the cleanup progress to the language. And by using a long jump and set jump that is can be widely used in C. It is a topic to be discussed on, but it's usable. Then we basically, if we would have used that in C++, we would basically break the contract between the user and the language. I also want to just clarify two terms that we're going to widely use. So there's a happy path, which is the default scenario with no exceptions or error, and the sad path. And here in this talk, I've mainly explored the sad path. Just as a side note, MSVC actually supports a different behavior in set jump and long jump, etc. But that would be something that is unique to their implementation. It's not something that is saddled between different implementations. So I've created a mini benchmark for exceptions versus error code. And again, I'm only focusing on the sad path. And you can see here that I'm returning I'm throwing 3 types of exceptions versus returning 3 different error codes. And you can see that the size of the error code. So this is the throwing 3 exceptions, and this is return value. And you can see it's rather close on hosted devices, but on embedded systems, I've used in this example on ARM, you can see that it makes a great difference. And another thing that you can see here is the difference on runtime, which is by no doubt is like a significant difference between those two ways. And as I mentioned, the clear observation is, I mean, you could do this benchmark on your systems, and you know, if it's this example is with Linux OS, but you could use it also try to do a sort of things in your systems. But I'm pretty confident that you're going to get similar results, or at least the major general notion of. So I'm sure we're clear on having the fact that exceptions are slower than the return values. And also, as I mentioned, it depends on your system. You might find a bigger difference. So there's 2 main implementations for exception mechanism. Now we're going to go deeper into how are they implemented. So the first one is table-based. So GCC and Clang, they both use this method. And I focused on this because it's creating better results on Happy Path. Now, again, I haven't addressed in this talk to Happy Path benchmarking, but I think it's makes more sense to have this assumption, because we want to have the regular code run as you'd hope, with better performance, and the code that fails, the error handling, to be slower. But it's of course up to your system. I just felt they more suitable and also aligned with the assumptions that we've seen in the history part. The other option is frame-based, and it's used by MSVC. And this one gives better set path results. So table-based implementation have the additional overhead or addings to the program. So first of all, we have to have RTTI in order to identify the exception type that is thrown. And another thing is the exception handlers have to be defined. And again, on GCC implementations, there's something that's called landing pads. So you have to basically add a function, a callback, to handle the exceptions. And it catching function contains additional information. So you have to be able to tell which of your functions which catch can catch this type of exception. So this is additional information that is kept regarding the functions. So I've added here the general, just you'll be able to see the amount of code So basically, the functionality is split into two main libraries. So you have libgcc, which contains the functionality of stack unwinding, and the libstd++, and again, this is on GCC, and it contains the functionality of exception handling. So again, you can see here the amount of code, and the mechanism is quite complex. So the stages of exception raising. So first of all, we allocate the exception by calling allocate exception function. Then we throw. Then we move to the lookup phase, which is the phase in which we're looking for the function that can handle our exception. And at last, in case we found this function, we move to the cleanup phase, which is the phase which calls all the cleanup functionality per frame. So in case of a failure, the exceptions can be allocated with unlimited size, but in case you can't allocate the exception because your system is low on memory, then you have some kind of an emergency buffer, and it's also limited to up to 4 exceptions. And there's additional conditions that regards to multi-threaded environment, but again, I said I won't be focusing on it here. But in general, you could end up with problem activating this mechanism. As we probably all know, one of the problems of exceptions is the fact that they're undeterministic. So we basically don't have a higher bar to limiting the overhead for the mechanism. So the stages of exception raising. So as I mentioned, we would start with the lookup phase, and we trigger stack unwinding with the flag of unwind whereas exception. With the flag of search phase for the function unwind whereas exceptions. And in case we fail, we call to std terminate. And in case we succeed, we get we get the handler found, and then we start the cleanup phase. So the cleanup phase is basically calling the same routine with cleanup phase. And the cleaning, we start with calling the personality routine that I think I've mentioned before. It's similar to it's the part that actually handles the exception. And once we finished cleaning the specific function, we continue with unwind resume. When we reach the stack frame with the proper catch, we're calling begin catch, and this is actually the thing that's supposed to treat the exception. And then we call the end catch, and in case we fail for some reason to deal with the exception, we might terminate. And if we also haven't found the proper implementation, if we need to move the past tense exception on, we can also call rethrow. And eventually, we'll continue unwinding. So I did a small draw because I think this makes things clearer. So as I mentioned, let's quickly go over the progress. So we have allocating the exception by the subroutine in case this subroutine was the one that failed. And then we, in case we can't allocate, we terminate the program. In case we succeed, we continue. Then we throw, and we start the lookup phase, and we go over up the stack and look for the catch that actually handles our exception. If we haven't found, again, we terminate. If we have, we go back to the first subroutine. We go back to the beginning of the stack, and then we start the cleanup phase. And as I mentioned, we look for the catch, and we catch. and in case we found a catch, we resume the execution, but after that, we look for the finally block if it exists, and if it doesn't, we just resume execution. So I'll just this is a small, shorter version of my talk, so I want to briefly go over the designs decisions that were made, but I also want to address the general principle that I'm sure, again, you're familiar with. Different types of errors needs to be handled differently in the program. So, on general, the general direction of the committee, and you can see it in Herb's paper as well, is to have to minimize the use of exceptions to the ones that actually are actually relevant. So basically, we don't want to throw logic errors, and we don't want to throw recoverable errors as exceptions. We might want to consider dealing with them as part of the logic or as part of the other ways to deal with failures in our program. And the things that should be focused on are errors that invalidate the program or errors that exhaust resources. So again, these are all the assumptions that were made regarding the first mechanism. I just want to focus on the ones on red here that are marked. So and again, this is from the basic design. So we want to be able to catch a group of exceptions. We want to be able to catch arbitrary amount of information, and exceptions used primarily for error handling. So I think we might want to consider to catch a single type of exception. The amount can be limited to suit to our embedded systems, and instead of having using this primarily, only be used for error handling. So we'll avoid things like logic manipulating throughout the exception mechanism. I mean, it's clear, but some languages might do it differently. So there are some projects that actually use the try-catch blocks to handle the logics. So I would assume we don't want to use it. We don't want to do that on C++. So general review on what I think we should do regarding this this mechanism. So there's a subroutine and the one that wraps it up, and the program wraps both of them. Sometimes we have the OS and we have the platform, and these are all true for old types of embedded systems. But today we have sometimes additional things. For example, we can have the connection to the cloud. So we basically could decide that in case of an error, we're going to send the information outside. And we also have, more commonly, since resources have been increased, we also have additional programs. And we could also have additional platforms. So I'm just going to read this quote again from the Design and Evolution, and I really agree with it. No single unit of a system can recover from every error that might happen to it and every bit of violence that might be done to it from the outside. In extreme cases, power will fail or memory location will change and its value with no apparent reason. So we need to be able to identify which are the errors that we want to have dealt with in our program and which ones are things that beyond the scope. So to move to the alternatives. Some techniques of exception mechanism can improve your performance, the exception mechanism performance in your code. So you could basically use the current mechanism and optimize, for example, by minimizing the number of exceptions, the different types of exceptions. You could override function calls from libstud, C++. You could re-implement parts of libstud C++, and these are, of course, going more advanced topics and advanced work, but it all depends on your on the things that you need in your system. And you can use alternative mechanisms such as MSVC's structured exception handling mechanism. So I basically focused on 1 and 2. So this is an example of code that is trying to minimize the number of different error types thrown. And you can see here that, so first of all, throwing one type of exception compared to return. So you can see here that the ratio is actually increased. So this shows us that just by adding the exception mechanism, we already get the penalty. And it doesn't really matter if you use a single type of exceptions or multiple types of exceptions. This is the thing that creates the overhead. And the size is again quite similar, though here you can see a bigger difference. And you can see on ARM again that the size difference is bigger. And if we'll compare to throwing different types of exceptions, then you can see this is quite close ratios. And again, this is from my own platform. You can also test it in your platform. So I'll generally say that from here we can learn that the overhead is added just by adding the exception mechanism, and that just limiting to minimize the different types of exceptions thrown is not significant, though I would expect that in a big project, of course, this is just a code that was created specifically for the example. So I would expect that on different code bases, might be different results. So I would recommend you to test it. So the second thing I've tried was creating the overloads for the libstud C++. And in this case, we can see here that there's functions throwing. And you can see that the throwing function is throwing some kind of exception. And we're hiding the functions that we saw before for allocate exceptions and throw. All right, and here you can see the size of the exception. I'll show it on the next slide, but basically I've also used a predefined buffer for the exception instead of dynamic allocation. So this is the allocate exception function, and in case it fails to allocate, it terminates. Otherwise, it returns. Otherwise it returns the buffer. Of course, it can be every type of a fail. We can basically decide what we define as a failure. And here we can have we can see the throw function, and it basically doesn't do much. So we could add here write to file or report to server or any other thing that's suitable for your specific environment that we wanna use, and then we exit. Of course, we could exit not with success, but with other things. And here, as I mentioned, you can see the size of the buffer that is defined globally, so it's not dynamically allocated. And you can see the call for constructor and fail and exit. So comparing this thin throwing version to throwing an exception, a single exception, I get the ratio that is very similar to what we saw for return values versus exceptions. And that means that the thin throw is actually, the thin throw is very close to the return value in performance-wise, runtime performance-wise. Of course, the size is still something that is added, since we still get the RTTI and the landing parts functions and the functions that can identify whether the exception belongs to them or not. But it's still, I think it's still very significant findings. So I think it's interesting to get a performance again so similar to the one for the return. And again, this is not a production level code, but this is trying to show we can actually customize the mechanism. So here, I just want to show my ideal throw. So I would hope that in the future standard, we're going to get some type of throw that we can customize and pass some kind of a callback or functionality to it in order to determine, do we want this failure to perform the unwinding, etc. And here in this code, you can basically see that the subroutine is passing the information to the program. But we could also define this globally. And in that case, the program will definitely basically define the handling mechanism to the subroutines underneath it. So let's focus on shortly on the few alternatives currently exist in the committee. So the first one, as I mentioned, is the zero overhead deterministic exception thrown values. Herb is proposing a few different things here. So first of all, he's proposing that first of all, he identifies that we use exceptions too much in different places that were originally addressed. So again, using exception for logic errors would probably give us very bad performance, and we don't need to use them to manage the flow. And another thing that he mentions is that allocation failures, or what I've previously addressed as exhausting the resources, is a different type of exception, different type of error that we actually we might want to use this mechanism for, because this type of an error says that we can continue executing. And we also have some concrete proposals regarding the performance. So he basically suggests, and this is common. This is relatively common nowadays. At least there's a library called Outcome that also doing this specific thing. But he basically suggests to have some kind of a union that returned from the function, and this contains either success or error, the values for the success, or the error in case of a failure, and a boolean that suggests which one is it. And I just want to emphasize here, this is of course returned on the stack, and this is not something that the developer should implement. This is a code that would be implemented from the compiler in this example, and unlike Outcome, for example. And it also suggests that we could predefine the allocator to report the error or to do other things. And I think the notion of having the error mechanism to be suitable for your own program is something that is widely addressed in the committee nowadays. I would hope that we'll get a more customizable mechanism in the future. So as I mentioned again, comparing to what we saw previously, here the program is basically defining to the different subroutines how to handle the errors. And the other paper that I've mentioned, Lowcost deterministic exceptions, is also very interesting and very promising. This is actually showing implementation for trying to implement some of the things that Herb have mentioned in his paper. And we get here replacing allocated exceptions on things that are returned on the stack or kept on the stack. And there's also some globally allocated memory here to deal with to help the mechanism, but it's basically a limited size buffer. And we can also rethrow by using this buffer, globally allocated buffer, and again, some of the principles that were addressed in Herb's paper are implemented here with and showing promising results. So I want to conclude with saying that you can create your own alternatives. You could signal to a different progress, or report to the cloud, or write to file. And you could use pre-allocated space, as I've shown, just by overriding or hiding the function that is in charge of allocating the exception. You could have save the minimal data that is needed. For example, and this is an extreme idea for certain cases, probably only suitable for certain machines, but you could decide you could sort of define a table with numbers, and each number can identify a different error or even different location in your program, and you could just return this single identifier if you think that it's useful for your code. So there's really different ways to address and to optimize this mechanism, this current version of mechanism. But again, I would hope that in the future the standard will address it and we'll have some better alternatives. Okay, so there again, as I've said, other mentioning of things in the standard that relates to the error handling mechanism, and I don't want to go too much into details here because this one's a shorter version of the talk. But I just want to mention that there's some very promising directions, and Bloomberg is addressing how do we address errors on debug mode or on development stage versus the release code. And there's also people in the committee that addresses the question of who determines the error. So do we want to handle the error in the same place in which we got it, or do we want to handle the error up the stack? And just to conclude, I think we should separate the semantics from the implementation. I think we should allow behavior suitable for the performance-sensitive applications. So we should allow more customizable systems. And the overhead already exists, and we already have the current mechanism already have its overhead. So by having more customizable parts of the system, we might get even a better results for broader spectrum of users. And just to again to I want to repeat this notion that the error handling mechanism was really designed quite long ago, and C++ is turning 30. So we have to consider the differences that were made in embedded systems in the past 30 years, and we have to address this 50% of embedded developers that don't use the current mechanism. And I think we should really consider the bigger picture. I also added here the developer crust because I think that's more commonly these days we don't have someone that actually looks on the errors or even the logs. So we have automated mechanisms that collect the data and we can have searches on these databases or whatever. So it's also quite more common to have those types of error handling environments. And to conclude, I invite you all to share your ideas with me regarding the ideal exception usage. I invite you all to get these notions and to take them forward and to I think that it would be very helpful for the committee and for the progress of C++ if many people as possible would try and address those issues, those hard problems, and give their input. And I suggest that we'll rebase the exception handling mechanism on our code, on a current computing mechanism that currently exists. And thank you. These are all the links that I've mentioned, and there's really a lot of very, very interesting links here. I just want to mention the proposal by Ben Craig, two proposals by Ben Craig that do a more broader benchmark on embedded systems, and they're very interesting to observe. So I really recommend you to go and look at them. And I invite you all to send me your responses and your ideas regarding this. Thank you.